For section 2.6, we're going to be looking at rational functions. Specifically, we're going to be talking about asymptotes and wholes. So basically, we're going to be looking at what is a rational function, and then where do these functions kind of, as we would say in math, blow up or go off to infinity, and where are there places where they have holes or openings within the function. So in this section, we're going to learn about the equation's horizontal asymptotes. We're going to look at vertical asymptotes, find locations where there are holes, and basically come up with a systematic method to graph a rational function using all of the above. So first off, what is a rational function? Well, rational function is a function that is of the form p of x divided by q of x, where p and q are polynomials. So something as simple as, say, x squared plus 10 divided by x cubed minus x, for instance. That is a rational function. Of course, q of x cannot be 0, because if it was, then we'd be dividing by 0, and we all know that's not okay. The graphs of many rational functions have what we called asymptotes. So you may have been wondering, what is an asymptote? An asymptote is a place where a graph approaches a particular value, but never actually reaches that value. So for instance, we'll see graphs here in a second that look like this, where you might have one side on this and then another one over here. It's a very rough sketch, but the y-axis in that case would be called an asymptote. So on both sides of the equation, we never touch the axis. Right, next, we have this arrow notation, and the key here realistically is that the arrow just means approaches. And this is something that, and you might get tired of hearing me say this, but this is something that you're going to use quite often in calculus. So when you get to calculus, you'll talk about limits that'll use these this arrow notation. But for right now, the arrow means approaches. The plus sign means from the right, and the minus sign there means from the left. Okay? So keep that in mind. We can also have x approaching infinity, which really just means x increases without bound or goes on forever to the right. And as x approaches negative infinity, that means as x decreases without bound or all the way to the left. All right? How does this related to asymptotes and wholes? So a line x equals a is a vertical asymptote if the function approaches infinity or negative infinity as x approaches some constant. The line y equals b is a horizontal asymptote if the function approaches b as x approaches infinity or negative infinity. So I'm going to go ahead and scroll down here to one of these equations so we can actually see what that means. Because a lot of times the sentences don't really mean much without a picture. So the first one, x equals a is a vertical asymptote. Okay, so let's look at a thing here. Here's a good example. You'll see we have a vertical asymptote at x equals -2. Above it said that the function goes off to infinity or negative infinity. Remember, f of x just means y. So what does the y value do as we approach this line? Well, from the left, it's going off unbounded to infinity. If we're looking from the right, as we come in towards x equal -2, this goes off to negative infinity. Okay, so that creates a vertical asymptote. Let's look at the other definition again. It says the line y equals b is a horizontal asymptote if the y value approaches b as x is going off to infinity or negative infinity. Okay. Again, looking at this example, as x keeps going on forever to the right, you see that this function is approaching y equals 3. And on the left-hand side, if we look at this as x goes off towards negative infinity, or as far as we can look to the left, the function is still approaching y equals 3. However, it never touches that line. That is why this is called an asymptote. Okay. So those are kind of all of the rules. The question is now, how do we actually determine these, right? We can see them graphically. We know why they're asymptotes. How do we find them? So finding asymptotes algebraically. The vertical asymptotes are pretty simple. You just have to figure out where the denominator has a 0. So you would set the denominator equal to 0 and solve. For horizontal asymptotes, we have a couple different options. If the degree of the numerator is less than the degree of the denominator, then the line y equals 0 is a horizontal asymptote. So what does that mean? So if we had x plus stuff with decreasing values of x powers over, say, x squared, right? The numerator's degree is 1, the denominator's degree is 2. That follows this pattern, and that means that y equals 0 would be a horizontal asymptote. On the contrast, if the numerator's degree is greater than the denominator's degree, then there are no horizontal asymptotes. So for B, if the degree of the numerator is equal to degree of denominator, then the line y equals, and we take the leading coefficient of the numerator over the leading coefficient of the denominator, is a horizontal asymptote. All right, we're almost done with the rules here. We still have one more thing for holes in the graph, and then we can look at a few of the graphs below and look at those examples. So how do we find if there's a hole in the graph of a rational function? So a hole in the graph of a rational function occurs when a value is not in the domain of the function, but a vertical asymptote does not exist there. So remember that for a vertical asymptote, we set the denominator to 0 and solve. If the numerator and denominator, when factored, become or have a common factor, which we'll see in a moment, the root becomes a hole. So you'll see here it says these holes may be found by simplifying a rational function and identifying common factors between the numerator and denominator. So again, all of these definitions might be a little hard to grasp. We really got to get in and look at the problems. So let's just look at these examples here for these graphs, and then we can actually go ahead and try some. So to begin, we have this graph here. This graph is the function 1 over x. So if we're to break that down, okay, let's go back and look at our rules really quick. Vertical asymptotes of the function occur by finding the zeros of the denominator. So I would set the denominator, which is just x in this case, equal to 0, and I would solve. Well, there's not much solving to do there, right? I just get x equals 0. And x equals 0 is the same thing as the y-axis. So the y-axis is a vertical asymptote. Okay. Then where are the horizontal asymptotes? Well, going by the rules, we need to look and see. We have x to the first in the denominator. That's a higher degree than the numerator, which has x to the 0, if you will, up there. If the denominator's degree is higher, then the line y equals 0 is a horizontal asymptote. So degree of numerator is less than the degree of the denominator. So y equals 0 is our horizontal. Then it says, also note the end behavior as x approaches infinity and x approaches negative infinity. So as we approach infinity, or just keep going really far off to the right, or negative infinity going off really far to the left, you'll see that this function is approaching the x-axis, but never touches the x-axis. And so we would say that the function is approaching 0. And we'll find that when you get to calculus, you'll call that a limit. All right, let's take a look at the next one. Looking at this example, we have the function 3x plus 5 over x plus 2. The degree of the numerator is 1, and the degree of the denominator is 1. So if we look back up at our rules, if the degrees are equal, then the line y equals the leading coefficients quotient is a horizontal asymptote. So what is the leading coefficient of the numerator? Well, that's 3. The leading coefficient of the denominator is 1. So y equals 3 should be a horizontal asymptote. And if we look, there's the line y equals 3. Okay, how do we determine for the vertical asymptotes? Well, that was taking the denominator, setting it equal to 0, and solving. That gives us x equals -2. That should be a vertical asymptote. So if we look, x equals -2 is a vertical asymptote. And then again, it says note the end behavior as x approaches infinity and negative infinity. Well, as we go off really far, they're going to approach that asymptote, but never actually get to it. So they approach 3, right? The function here approaches 3, but never actually equals 3. All right. The last example here, a little bit more complicated functions. They have the same degree for the numerator and denominator. Therefore, the leading coefficients tell us what is the horizontal asymptote. So that would be 3 over 1. So this line right here is y equals 3. Furthermore, if we would like to find if there are any holes, then we need to factor the numerator and denominator. So you'll see the factored form just below here, and you'll see highlighted that we have x minus 5 over x minus 5. So x minus 5 is a factor in the denominator, and the root would be x equals 5. That also happens to be in the numerator. Because of this, this is not a vertical asymptote, but instead a hole. So that's what that was saying above, that you have to have the same factor in the numerator and denominator to get us a hole. The other factor, x plus 2, gives us our vertical asymptote. And because we set that equal to 0 and solve, that's actually x equal -2. The numerator also has x plus 1, which gives us x equal -1 as a root. And one thing we haven't actually talked about here is the y-intercept you can get from the constants at the end by just doing their division. All right, so that concludes all of the rules. Continue on to the next video to look at some of the examples.